very early this morning.
Yeah, so you did it before today's class. That's what matters.
At like 12:04, I think I turned it in.
Okay, yeah, that's fine.
Oh,
Um,
wait. It says, oh no, I clicked on the wrong thing. I turned it in at 12:16.
that's perfect. That is
Yeah, I
perfect.
have some questions about it.
Don't worry, we will go over all of them today, so you can never fear. Um,
Can I just ask you a couple questions now?
yes, go ahead.
Is there a kind of force that's like momentum? Like when like you hit a hockey puck and there's it's no longer like applied force, but like it's still moving to the right.
Okay,
But like I'm
so
not sure what like it's
uh,
called.
so what I want you to think about is the hockey puck is moving after you hit it. I agree. Is there anything physically pushing or pulling the hockey puck after you hit it?
Um, there's friction
There's
like
friction.
pulling it kind of.
Yeah, the
Or
friction, is
yeah.
slowing it down. But is there anything else that's pushing or pulling it?
That's where I'm kind of confused. I would think there
I,
like
I
I
want, I
don't
want you
think
to,
there's
I
anything.
want you to think about it. I don't want you to worry about like, the terminology here. I just want you to think about it. Is there anything actually physically pushing or pulling the hockey puck after you hit it?
I don't think so.
Okay, so if there's nothing physically pushing or pulling it, are there any forces acting on it that are pushing it or pulling it?
No.
hmm
Oh.
So that's a very important distinction, or not distinction, a very important interesting fact is that just because something is moving, it does not mean that there is necessarily a net force on it. And we will take a look at more of that today, a little bit when I go over it. But that's something that's very hard for a lot of people to sort of wrap their heads around, is the idea that something can be moving and have no net force on it. A force just means it's something basically pushing or pulling it. It's something slowing it down or speeding it up. After you hit a hockey puck, right, the only real force, well, there are three forces acting on, but the only like force that's important is friction. That's slowing it down. But there's nothing actually physically pushing your hockey puck forward. There's no engine on it. There's no like, you're not hitting anymore because you already hit it. So there's just nothing pushing it, keeping it going. So that's the distinction between the two. So
Oh, okay.
yeah, yeah. So when I go over the practice problems, I'll go over them as well. So never fear, you are all not, you will not be abandoned, my childs. Okay, so hello everybody. Welcome to another day of physics. So we are going to get started today with our warm up. So what I want you to do is I want you to, so there's a particular scenario here. I was trying to write a more interesting scenario, but like, I don't know. I was feeling my creativity was lacking. So I just wrote a very basic problem. So there's a car, 100-kilogram car that is accelerating to the right at 5 meters per second. And there's a force of friction acting on it. And that force of friction has a force of 200 newtons. What I want you to do right now is I want you to ignore air resistance, and I want you to draw a free body diagram for this scenario. Once you have a free body diagram, then I want you to try to find the normal force acting on the car and then the applied force on the engine. Once again, we have a car, a 100-kilogram car that is accelerating to the right at 5 meters per second. The force of friction on the car is 200 newtons. I want you to draw a free body diagram, then to find the applied force of the engine and the normal force.
Sorry, but don't cars like work because they have a lot of friction? Question
Sorry?
mark. Don't cars work because they have friction?
They do have a friction.
Because I'm pretty sure
It's
like when they roll, they don't really have any friction against them, because what they do is they push against the ground, and then the
Well,
ground pushes them back.
yeah. Okay, yeah. So there is friction against the car. That is definitely there is friction against the car. That friction is also what allows them to keep them going, as you were saying. So I just want you to treat it as like, you are like the engine is pushing it forward and then the friction is pushing against it. You are right that the contact between the tires and the ground is what allows the car to keep moving, because if the road was perfectly frictionless, the car would not actually be able to move. But that's like much more like complicated, and we won't quite go into the nuances of that. So for now, I just want you to treat it in general, like as in the engine is pushing it forward, and then the friction is pushing against it.
Oh, because I took like most of the free body diagrams as if, well, a car uses friction to move, so.
It does use friction to move. It does use friction to move, but it's not so much that the car uses friction to move. It's yep. The tires will put a, how do I describe this? When the wheel is rotating on the ground, because it's almost like, yeah, it's like basically the friction, because the wheels are rotating like this, there is going to be a friction induced on the tires going against it, and then that's going to create an opposite force. Well, there's going to be equal and opposite force going forward, which pushes the car forward. So the friction is a major part of why the car moves forward. But for the context of this problem, we're not gonna go quite into that complicated. Just treat it as like, you can, instead of a car, just treat it as like a block. The block is moving forward.
Okay.
Yeah. Once you have a free body diagram, I want you to find the normal force acting on the car and then the applied force from the engine. I'll take another minute or two to do so, and then I will start working through it on the board. That is true. That is true. I was more looking for numerical answers, but that is right. Right. The road, it does apply normal force, and then the gas is applying is the applied force, or is helping create the applied force. I was just more looking for like numerical answers here. So let's take another minute or two to work through this to the best of our ability. It's okay if you aren't super. One more minute. Okay, so let's first start with a free body diagram for the car. Okay, so in general, the free body diagram, you always want to start with the box because everything is a box in the real world. Okay, so how do I like to start a free body diagram? Well, the first thing we want to do is let's think about it, and let's think about what forces are acting on our car here. So first off, in life, in the real world, the force of gravity always exists. So right off the bat, you already know that there's one force acting upon it. Okay. Then I want you to think, is my car accelerating up or down? And the reality is, no, it's not accelerating up or down, which means that in order to balance out this downwards force, there needs to be some sort of upwards force balancing the car. So let's think about what is balancing, what is keeping the car from falling? Well, that's the road, right? The car is on a road, and the car is pushing into the road, and the road will push into the car and keep the car above ground. So what is that force called? Well, that's a support force. The road is putting a support force on the car to keep it above ground. And so this is what we call a normal force. So with these two forces, they're the same size arrows, and this tells us that the car is neither accelerating nor decelerating upwards. Okay, so what else do we need? Well, we know that the car is accelerating to the right. So we know that there has to be some sort of applied force here. And we know that from the problem that there is a force of friction, and the force of friction always opposes motion. So we're gonna have a force of friction here. So we want the rightwards arrow to be bigger than the leftwards arrow because the car is accelerating to the right, which means that overall a net force should be towards the right. So this is just the free body diagram for the car. This helps us a lot in terms of figuring out how to find these forces. So what should we do next? The next thing we want to do is we want to figure out what our normal force is and then what our applied force is. So what forces and acceleration are, well, and in motion in general, are similar because they both work within 2 dimensions. Similar to how when we did our 2-dimensional projectile motion, we worked in both the y dimension and the x dimension. We also want to be working in the y dimension and the x dimension for forces. We want to find all the forces acting in our y direction and all of the forces acting in our x direction. The forces acting in our y direction do not impact the forces in our x direction, and the forces in our x direction do not impact the forces in our y direction. So how do we do this? So we have a free body diagram right here that already tells us what are all the forces in our y direction and what are all the forces in our x direction. So let's first start off with using Newton's second law. Newton's second law is saying, it says that the net force is equal to the mass times the acceleration. And so what we're going to use, we're going to use Newton's second law, and we're going to use it for both the y direction and the x direction. And we're going to keep them separate of each other. So what do I mean by this? What I mean is that the net force in the y direction is equal to the mass times the acceleration in the y direction. And then the net force in the x direction is equal to the mass times the acceleration in the x direction. So first off, what is my net force in the y direction? Well, the 2 forces that comprise my net force in the y direction is my normal force, which is going upwards, and my gravitational force, which is going downwards. Right? So one of those will be positive, the other will be not negative, and the sum of the difference between the 2 is our net force in the y direction. And this is equal to our mass times our acceleration in the y direction. Now let's think for a second. Is our car accelerating in the y direction? No, because our car is neither accelerating nor decelerating upwards, which means that our acceleration in the y direction is going to be 0. So this whole thing is equal to 0. So our net force minus our gravitational force is 0. In other words, our net force in the y direction is equal to 0, which means that our normal force should equal my gravitational force. Which makes sense, right? However much force gravity is pulling down my car, the road needs to exert the same amount of force to keep my car above ground. So how do I figure out my gravitational force? Well, this is just my mass times gravity, gravitational acceleration constant. The normal force is just equal to this, which is 108. So my gravitational force, my normal force should be 980 newtons. Right? So my gravity is pulling down my car with a force of 980 newtons, which means the road needs to exert the same amount of force to keep it upwards. So
I have a quick question. So we have something like there's a document on Canvas. It's called like friction graphic organizer. should we put like our warm up on there because they have a different warm up?
No. That's we'll do that. We'll do that later today.
Okay.
So that's like a
do we
second
want
warm-up.
to record these answers anywhere or no?
No, you don't. You don't have to record these answers anywhere.
Okay.
But I would write them down just as your own reference. But there's nowhere you need to write these down.
Okay. Thanks.
Okay. Okay. So now we figured out our force in the net force in the y direction. I think the y direction is a lot simpler. I think our x direction is going to be a lot messier. So first off, we already know what my car is accelerating in the y direction is. My x direction acceleration is, is 5 meters per second squared. Right, this is because I gave this to you. So my net force in the x direction is equal to my mass times my acceleration in the x direction. And this is what my net force is. So overall, the net force in my x direction should equal 500 newtons. Now, does this mean that my applied force is 500 newtons? No, it does not. It means that my net force, in other words, the combination of my friction force and my applied force, the combination of the two should equal 500 newtons. Okay, so now let's break down what our net force should look like. So I have one force pushing my car to the right, so that is my applied force. And I also have a frictional force pushing my car backwards. And the combination of these two forces will equal 500 newtons. Because one of these forces is pushing forwards, and one of these forces is pushing backwards. So the frictional force is 200 newtons, as given. Which means that my applied force should be 700 newtons. So notice here that my net force is not the same thing as my applied force. My net force is like my overall force. After I include all of the forces and pushing against me, pushing with me, after I include all of these forces, that is my net force. My applied force is just how much force is the engine pushing the car with. And so the net force in this of the car is how much force my engine is pushing with minus how much the force of friction is pulling my car back. And so that I get that my car's applied force is 700 newtons, not 500 newtons. Okay. Does anyone have any questions?
Where'd you get the 200 from on the?
It's given. It's given in the problem.
Oh, okay.
So the final answer is 700, right?
Yep.
Okay.
So in general, this is more or less the general setup for any sort of force problem. You pretty much do exactly this. You set up a free body diagram, you analyze all of the net force in the y direction, you analyze the net force in the x direction, and then you use that to figure out whatever you're looking for. So this right here, this general setup is pretty much what you'll be doing for the rest of eternity. You will memorize. Okay, I don't want you to memorize it because that just means like you don't know. I just mean just get a feel for how to do this, and you'll be doing this a lot because this is the general idea for things. Okay. So if you don't have any other questions, what I'm going to do now is I'm going to review the free body diagram practice problems that you hopefully were able to do. If you weren't able to do them, that's okay. I'm just going to review them and go over each one. So I'll give you a minute to pull up your free body diagram practice problems. I'm going to leave this up for now, and then I will erase it as I go through the free body practice problems. So Okay, so the first free body practice problem, free body diagram practice problems, talks about a parachute on a guy or girl or human or dog or whatever that is falling down. So we have a parachute, we have a guy or a girl or a person falling down, which means that there is a force of gravity acting on this person. So what other forces are acting on this person? Well, if you want to, let's think about how a parachute works. A parachute works, right? Because you make this like giant thing that increases the surface area, so that way you can essentially catch more air to basically increase your air resistance, so that way you slow down more. So parachutes work with air resistance. The bigger your parachute, the more air resistance you have, and the slower you will go. So when the parachute person opens his parachute, basically he's increasing the amount of air resistance he has, which allows them to slow down. And in this particular case, they are physically slowing down, which means that the air resistance force going upwards should actually be bigger than the gravitational force going down. So the person is being pulled down by gravity. They also have an air resistance force going upwards that is bigger than the force of gravity going down. Okay, so let's analyze this for a second. The person is falling still, but they are accelerating upwards. So how does that work? Well, if you think about it, my velocity is essentially negative as I'm going downwards, right? Because I'm falling towards the ground. And having a positive acceleration means that my velocity is becoming less negative. It's becoming closer and closer to zero. And so that's essentially what's happening here. You're slowing down even though you're still moving down. And that's the force of air resistance, which is bigger than our force of gravity. What else do we need? We also have a stiff wind blowing from the right. This wind is essentially, if it's blowing from the right, it's going to push you to the left. And so this wind is going to apply a force, applied force to the left. So your free body diagram should look something like this, where you have the force of gravity on the skydiver going down. You have the air resistance force going upwards that is bigger than the force of gravity going down. And then you have an applied force going to the left. Does anyone have any questions on this first one?
Is there no force between the backpack and the person, or the tension between the string that would be holding the parachute?
Okay. All right. So let's get technical for a second. So the reality is, how do I draw this person? It's like this.
I mean, you could assume that he's directly holding onto the parachute.
Okay. So yes. Okay. So technically, what happened is that the person has a force of gravity pushing down, and technically, it's the parachute itself has air resistance, and the parachute is applying a tension to the person that keeps him up, that keeps him from going down. So technically, if the parachute is connected to the person through like strings, then technically it would be tension. Now, as Soke was saying, if the person was holding on to the parachute like this, instead of like with a string, with like, you know, ropes or strings attached to it, then it would be just air resistance in general. I think we don't need to go quite into like, okay, the thing with tension is that like technically this stuff like this happens all the time where it's like technically it's tension. Unless the problem explicitly says like some sort of cable or string or something, then I don't really want you to worry about tension, because it's a little bit more complicated. But yes, if the parachute was attached to the person via like, you know, strings or whatever, then it would be tension. But if the person was physically holding onto the parachute, which doesn't really happen, but if it was, then it would be just air resistance. Yeah. So tension, as you'll see, or we won't quite get to it yet, but tension, as you see, it can get very messy very quickly. Because there's a lot of things that it's technically, that it is tension that's doing the work and not something else. But yeah. Okay, so speaking of tension, guess what the next problem involves? You guessed it, tension. So we have a piano here that is going downwards and it's being lowered at a constant velocity. Okay, so first off, as always, there's a force of gravity pulling down the piano. Because the piano is being lowered at a constant velocity, constant v, is no net force. This means that we have to have an upwards force that is equal in size to the downwards force. Okay, so what is this upwards force being applied on the piano? It is not a normal force. It is not a normal force because the piano is not physically resting on something. Instead, what's keeping the piano up is the cable. And a cable has something we call a tension force. So this cable is what's keeping the piano from falling and applying an upwards force equal in size to the downwards force. Question 3, very similar, except this time the piano is accelerating towards the ground, which means that instead of the forces being equal, the tension force needs to be smaller than the gravitational force. That way the piano can accelerate towards the ground. So let's talk about number 4 next. Number 4 is our hockey puck gliding across the ice. So this one is probably probably a pretty tricky one because again, it's very counterintuitive. So let's talk about the hockey puck first. What are the forces acting on it? Well, immediately we know that there's a force of gravity acting on it. Is the hockey puck accelerating up or down? Up or down? No, right? It's sitting on ice, which means that the ice is going to be putting a normal force on the hockey puck, equal in size to the gravitational force. And then the hockey puck is now on a rough patch of ice, which means that it's going to be, it's going to slow down a little bit because of friction. And so there's going to be friction force pushing against the hockey puck. And then there is no applied force on the hockey puck because you already hit it. There's nothing pushing it anymore. So even though the hockey puck is still moving forwards, there's no force pushing it forwards, right? Moving forwards doesn't mean that there is an applied force.
Is there any momentum? Or does that
It
not?
does have momentum, and momentum is related to inertia. Because it's moving forwards, it's going to stay moving forwards, but it doesn't mean that there is a force acting on it.
Okay.
It's like you already roll the ball. You don't have to do anything else to keep it from rolling. You actually have to do something in order to slow it. But
Okay.
you don't have to do anything to keep it moving. Which is the same idea here. Yeah. The momentum of the hockey puck is what's keeping it moving, but there's no force acting on it. There's nothing pushing or pulling it, other than friction. Okay, so 5. The car is accelerating towards the right as it's driving along the street. So I think we did this problem and for the warm-up, right? If you have a car accelerating towards the right, you have applied force, you have a smaller friction force to the left, you have a normal force going upwards, and you have a gravitational force going downwards. Question 6. A stalled car is being pushed at a constant velocity. Once again, constant velocity means that there's no net force. So the force, there's a normal force and a gravitational force because it's not going up or down. It's not accelerating up or down. And then the applied force by the people to the left is going to be the same as the frictional force to the right because it is at constant velocity. Okay, so these two are going to be, the next two are also going to be very tricky. for different reasons. So this one, you kick a soccer ball, and then it's now it's at the apex of its trajectory, and then it starts falling. Doesn't the rough patch of ice stop the puck? Yes, it slowly stops the puck, right? So it's not like when the hockey puck hits a rough patch of ice, it doesn't stop it immediately, right? It takes time to slow it down. It's applying a frictional force that's slowing down the puck and eventually stopping it theoretically. So it does work. The frictional force is what's going to be slowing down and eventually stopping the puck, but it doesn't stop instantaneously. The point of this free body diagram is to show that the rough patch of ice is applying a frictional force on the hockey puck that slows it down over time. And if it stays on the rough patch of ice long enough, it will eventually stop it. So yes, hopefully that answered your question. It does work to try to stop the puck.
Also, for
But-
number 5, is there any air resistance?
Okay, yes, yeah, technically there is. Technically there is air resistance. So technically there is air resistance here. If you didn't put air resistance, that's okay. I wasn't really looking for it. Technically, with any problem that if you're moving, technically there's always air resistance. So if you put air resistance in these, then that's like you could have put air resistance for the piano ones. That technically would have been fine. I just wasn't really looking for it because it's just, it's sometimes air resistance can be complicated and it's not always super practical. But yes, there technically is air resistance for the car. Did I answer your question about the rough patch of ice? Okay, so let's go to the soccer ball one. So the soccer ball is kicked in the air. As always, there's always the force of gravity. And then once it's in the air, that's it. There's nothing else. There's no air resistance because we said to ignore air resistance. I said to ignore air resistance. There's no friction because the car ball isn't on the ground. There's no normal force because it's not on the ground. There's no applied force because you already kicked the soccer ball. So there's just the force of gravity. It's essentially in free fall. I mean, it is in free fall. It is in free fall. 8. Okay. This backpack one will be subject to a little bit of interpretation depending on how you visualize this. So I would do 2 possible free body diagrams depending on how you visualize this. So let's call this visualization 1. Let's imagine this is your chair, right? So let's imagine if you were that the backpack is on the edge of the seat. Edge of the seat. So as soon as the car stops moving, or as soon as the seat has a force moving to the left, right, the backpack is no longer going to be sitting on the seat. So which means that because the backpack is no longer sitting on the seat, there's only going to be a gravitational force pulling it down. There's no more normal force because it's no longer sitting on the seat. There's no frictional force because it's not sitting on the seat. And there's no applied force because there's nothing. The seat of the car is slowing down. The car is slowing down. But the backpack is not because there's no force. There's nothing. The backpack itself is not attached to anything. So there's no force on the backpack. So it's just the force of gravity. Now, if you also interpret it as the backpack is on the back of the seat, and then it's slowing down, then in which case you can say that there is a normal force in the backpack in the seat, and that there is also a frictional force. So both of these are accurate. It just depends on how you interpreted the problem. Okay. Does anyone have any questions on these? Okay. So hopefully I went through these at a reasonable pace. If you have any questions, you can always let me know. What we are going to do today is we are going to do a little bit more continued instruction. We're really going to analyze the force of friction today, and we're going to actually look at how we can calculate it. So to start off here, there is going to be a graphic organizer for you to fill out. As I start with something. As I start with the next set of slides. Okay. Okay. So this as a very, 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 very just quick, easy form of, just want you to quickly just answer which of the following surfaces do you think which of the following surfaces do you think has the most friction?
Do we think that wood has splinters in them or like weird spots?
Let's treat it as like, imagine if it's like a wood floor. Take another 30 seconds or so. It's okay if you aren't sure, take your best stab. I'm just very curious to see what you think. Okay, so it seems that we have a split between grass and asphalt. We have a few people who believe that concrete has the most friction, and we have some people who believe that wood has the most friction. This question was not specific enough, so it's up to some interpretation. But we will look at what it means to have the most friction on things. So the answer is I won't tell you because it sort of depends. But it's good to think about which one has the most friction. So what we will do today is we will look at friction today, and I don't know if we'll start the assignment today, but we'll see if we can. What we're going to do is we're going to try to analyze how friction affects the motion of objects. And the assignment will be due next week, but we may not start it today. We'll see. Okay, so what I'm going to do is there is a demo that's, well, I can do it too, but you can also, there's also a video that I have as well that will also demonstrate it. Okay, so basically, let me just quickly show you what I'm talking about. Okay, so in this demo, hello. Okay, so you have a meter stick like this. And the demo is basically asking what happens if I hold the meter stick with my two hands and I start sliding one hand towards the other. So I'm not going to be gripping it with one hand, I'm going to be sliding towards the other. And I want you to write down what you think is going to happen. All I'm doing is I have my meter stick in two hands, and I want you to write down what you think is going to happen as I move one hand towards the other. So it'll take a few minutes for you to write down. If you have something to share in the Zoom chat, I would love to hear what you think. We will be revising or revisiting our predictions and hypotheses. So I don't expect you to know what's going to happen. Oh. There should be a space in the graphic organizer for you to just quickly jot down what you think is going to happen. Do you think it's going to tumble over? Do you think it's going to smack me in the face? Do you think that it's meter stick going to break? What do you think is going to happen when you start sliding one hand towards the other? The thing is, you don't have to do it with a meter stick. You can do it with like a pencil. It works with a pencil. It works with like honestly, it works with any sort of object you can hold between your two hands. You can try it as well. You can follow along as well if you have something. I mean, I would try with your pencil. If you have a ruler at hand, if you have a A calculator? I think it probably works with a calculator too. Yeah, it works with a calculator too. It honestly works with anything that you have in here. So I would actually recommend you try to follow along here. So take another minute for you to write down what you think is going to happen when you have a meter stick and you start sliding one hand towards the other. I have a ruler here that you can try. Okay, so let's look at what happens when you start sliding one hand towards the other. Okay, so I'm going to do it in front of you as well. There's a few things going on in here, but the main thing we want to look at is basically you have a meter stick or any sort of, honestly, any sort of lengthy object. You start sliding one thing toward the other. You might, so what happens is your hand is sliding over. And at some point, as you're sliding your hand over, the meter stick will stop sliding over your hand, and it'll instead start sliding over the other hand. So it sort of happens is my right hand is starting to slide first. And after a while, it'll sort of catch, it'll sort of stick, and it won't move anymore over my right hand. And then what will happen is it'll start automatically pushing it over my left hand. And then after a while, it'll stick on my left hand, and it'll start sliding over my right hand. And eventually it'll keep sort of like switching off. Like it'll start sliding over my right hand, it'll start sliding over my left hand, and eventually it'll just sort of meet at the middle. So it's sort of alternating which hand it slides over instead of tumbling it over. So what I want you to do now is I want you to try to create an explanation for the phenomenon. Why does the meter stick, why does it keep swapping over which hand? Why can't we just slide it over one hand the whole time? Why does it keep switching off which hand we're sliding over? So try to create an explanation for the phenomenon. And then when you're ready, share your explanations in the Zoom chat. Try to explain why the meter stick, why you can't just slide it over one hand the whole time. Why does it swap? Why does it go over one hand, go to the other hand, and then go back to the first hand? What is preventing it from just sliding the whole time? We got a good idea so far, like what I'm seeing. Can we get a few more ideas on what's going on here? It's okay. It's. I'm not looking for what is actually. I'm looking for what you think is happening. So, and we're going to revisit this later on today. So let's see if we can get a few more people to share with me what they think is happening here. Oh, I see. I see. So we have a couple of ones so far that I really like. I will share them out, but don't worry, I won't say who's doing what. Okay, so let's see what people are saying. So one person is saying, okay, gravity is pushing from both sides of the ruler. Therefore, there always need to be a balance, like a seesaw. Therefore, we can't slide one hand over, and that's absolutely true, right? We can't. We need to have, the ruler wants to be balanced. And that's very clever. Another person saying that the meter stick keeps on switching off between each hand because when there is more meter stick on one hand, there is more weight and then more friction, and then so the meter stick will shift to the other hand as it's pushed instead of the hand being able to smoothly go under the stick. That's very cool as well. Another person is saying that it's as you're sliding against your hand against the ruler, it's gaining friction, which sort of makes it stop, which is very interesting. Your hands will meet at the center because there's more friction on the side with more weight, so it won't move, but the other side will move. Because the weight of the meter stick is more distributed on one hand, the hand has more friction, so the meter stick will slide over the hand that has less friction. Ooh, very interesting. And your hand will move to one side, the weight acting on it increasing friction until that hand has too much friction, and the other hand starts moving. That hand has too much friction. Wow, these are some really good answers here, actually. So I really like what I'm seeing so far. And we will talk about this later on today. And then you will get a chance to revise or revisit your hypotheses and try to make it even stronger than what you just said. Okay. So very quickly, I just want you to think about this. I just want you to quickly write it down. What do you think it's harder to start a car or is it harder to keep it moving? And why do you think so? So this relates a lot to the ruler, right? This does relate a lot to the ruler. This one is a little bit more intuitive. Is it hard to start a car or is it hard to keep it moving? This does relate a lot to the ruler. So I want you to quickly jot down a moment what you think. Is it harder to start a car? Is it hard to keep it moving? Why do you think so? Actually, I should make a poll for this, really. Give me 1 second. I'm trying to make a poll here. Oops, wrong poll. Let's see, which poll do I want? Okay, so let's get a poll here. Let's get a quick poll here. Is it harder to start a car or is it harder to keep it moving? If you have any like more like thorough, like not thorough, but if you have any like explanations or why you think so, I would love to hear them as well. You don't have to, but I would love to hear why you think it's harder to start a car versus harder to keep it moving. Does anyone have any ideas why you think it's harder to start a car versus why you think it's harder to keep it moving?
Can I share my idea?
Yeah, go ahead.
So, for example, acceleration usually goes very slowly at first and then goes
Mhm.
faster and faster.
Mhm.
So that's one of the few proofs that I could say that acceleration is using acceleration, that it's harder to start a car than to stop it.
Mhm.
Uh,
Okay, I like that. Something to do with acceleration. It's very hard to sort of get it going initially, and then it gets faster and faster. We have a few people who used a couple of people who've said something about inertia. It requires more force to change its motion than it is to continue its motion. So that's Newton's first law. A motion object in motion stays in motion, whereas it takes more energy to go from stationary to moving. It's also a good answer. So we have a lot of ideas so far relating to inertia. Harder to start, and it's because you need to cancel out friction and apply additional force. To keep moving, you only need to cancel out the friction force. Very interesting as well. So I like what I'm seeing so far. I think one thing I really want to hone in on here is this idea of inertia. There's an idea of that something wants to do what it's doing. It do what it want to do, as Mr. Who philosophized once. So something that's doing something wants to do that something. So a car that is not moving wants to not move. A car that is moving wants to move. And so because of this, it's harder to start and stop a car than it is to keep it moving. And that's because of the concept of inertia. So a car wants to resist any changes in its motion. So a car that is not moving wants to stay not moving, and a car that is moving wants to stay moving. So it's very easy to just keep doing what it wants to do. It's very hard to start a car that is not starting. So part of the reason why it's harder to start and stop a car is because of something called friction. Friction plays a role in this. So the way that friction works is friction works by the way we think friction usually works is that, friction, an object that is moving, right, friction will slow it down because it's rubbing against it, which is true. Friction also works by keeping an object from moving. So in order to move an object that is not moving, you have to overcome the friction that is preventing it from moving. So friction does it does play a role in how easy it is to start and stop an object, and how much an object is being slowed down by friction. So to continue off this, what makes friction interesting is that friction is a reaction force exerted by a surface when an object moves across the surface. So this is what Soke was saying earlier. When the tire is on the ground, the tire is going to exert pressure on the ground because of the force of gravity. The ground is also going to exert a force onto the tires, and it's a resistance force. As the tires are moving forward, the ground is also resisting that forward motion, and that's resisting it through a reaction force called friction. And so, in other words, when a object acts on a surface, the surface reacts to the object via the friction force. Friction opposes the motion of an object. So if an object is moving to the right, the friction force will be directed to the left. Now, the amount of frictional force an object feels can vary quite a bit. So we talked about we talked a little bit about why it's harder to start and stop a car. And that's partially because of basically how much friction force an object has. What I want you to do is I want you to think about and try to, give an idea of what you think determines the amount of frictional force an object feels. And what would you think you would need to know in order to figure out how much friction force an object feels? So I take a few minutes to try to think about what do you think determines how much frictional force an object feels. Do all objects have the same frictional force? Does it depend on where you are? Does it depend on how long the object is? Does it depend on how fast the object is moving? Does it depend on how big the object is? Does it depend on how the shape of the object? What do you think determines the amount of friction force an object feels? And what do you think you would need to know in order to figure out this frictional force? If you want just sort of a little bit of context for this, right, with the ruler, what we're trying to examine is, right, what sort of determines how much friction force is present between your hand and the ruler. That's sort of a little bit of a context if you want to ground it in something. But I want you to think about what do you think determines how much a frictional force an object feels? If you have any ideas, I would love to hear them. We've had a lot of really good ideas on things so far. Any ideas on how much friction force an object has? You can also think about a warm-up question too, right? Which surface do you think has the most friction? Do you think that has an impact on how much frictional force an object feels? Do you think that a bigger object would have more or less friction than a smaller object? What are some things that you think can determine how much friction force an object feels? I would love to hear some ideas. We have one person who says, okay, it's got something to do with its mass and acceleration. There's someone that says, maybe it's determined by the mass of the object. Another person saying something to do with the normal force. Interesting. Anything else? Anything that is different than those? Anything else that you feel like matters? Surface area, mass and surface area. Interesting. The friction amount of the surface as well as the force applied on the surface. Interesting. I really like all your ideas so far. And so the terrain, whether or not it's rough or smooth, also very interesting. So I like what I'm hearing so far. So there are quite a bit of things that determines the amount of friction an object feels. It depends on how complicated you want. In the gist of it, the main two things that determines how much friction an object has is the mass and the surface it's on. Now there are some other things that will determine how much friction an object has. For example, the surface area of the object does determine how much friction it has, but that's harder to measure, at least especially within the context of this class. But in general, the two main things is the mass and then the type of the surface. So why does the mass affect how much friction you have? Well, more massive objects, because they're bigger, because gravity is going to pull them more, they're going to exert more force on the ground. And because every force has an equal and opposite reaction, this means that if you're pushing the ground harder, the ground is also going to push harder on you, which means that the normal force, in other words, the normal force of the ground is going to push more into the object. So basically, right, friction, it sort of depends a lot on how much contact an object is coming in with the ground. And so if you're pushing the ground more, the ground is going to push more onto you, which means that there's going to be more frictional force. And so if the ground is going to push more into the object, it's going to more strongly resist changes in motion, right? If you have a very light object, right, the ground is barely going to be pushing onto it, which means that there's not going to be a whole lot of friction there. Whereas if you have a semi-truck, right, it's very heavy, it's very big, it's going to be pushing a lot into the ground, which means the ground is also going to be pushing a lot into the semi-truck. It's going to more strongly resist it. So the mass of the object depends on it, but more specifically, the normal force of the object determines has a big impact on how much frictional force it has. So the mass and the normal force of the object is one key role, plays a key role in determining how much friction an object feels. Another thing that helps determine how much friction an object feels is the type of the surface it's on. So this is what the warm-up question was asking me out earlier. What surfaces do you think have more or less friction? So for example, ice and asphalt has very different amounts of friction. One might normally say that ice has less friction and asphalt has more friction. So we talked a little bit about, how do we think, what do we think determines the amount of friction? Now I want you to, and I was sort of saying, okay, we're sort of saying, okay, the mass determines a lot and the type of the surface, but why do you think different surfaces have different frictions, right? So I'm, like it sort of logically makes sense. Yeah, ice seems like it has a lot less friction than asphalt was intuitively, logically, but why do you think ice would have different frictions? And how do you think you would test this? Is there any way to test it? So let's focus on these questions here. Why do we think surfaces have different frictions? And how do we think we might test this? So why wouldn't ice and asphalt have the same amount of friction? Why wouldn't a wet road have the same amount of friction as a dry road? Right? What is changing the amount of friction a surface has? Why is it so easy to slip on a wet floor versus a dry floor? Why is it, why do, give me a minute to just sort of think about why you think surfaces have different frictions. This one I think is probably harder to sort of get a feel for. I think it's, ooh, interesting. I'll give you another minute or two to try to, take as much time as you need, but I want to try to see if we can get some more ideas here. We have one really good idea so far that I'm not going to share quite yet because I want the people to have a chance to share what they think. Does anyone have any else have any ideas? Why do we think surfaces have different frictions? Right? It's like if you've ever tried ice skating on a rink, right? Why is it so much easier to skate on it when when the Zamboni, like when the Zamboni just freshly not paves the ice, but like resurfaces the ice, it's really easy to ice skate on it. But when the ice is really rough, it's really hard to ice skate on it. Or why is it so easy to skate on, like really soft snow versus really hard surfaces? So a couple of ideas we have so far is we have something. So we have one person we have one idea where it's something to do with the state of the matter and the molecular components of a surface, which are all different. So something to do with the state of the matter. How is the surface? How is the molecular arrangement of the surface? What is that sort of related to? And then we feel like we can test it by taking an object and applying the same force on different surfaces and measure the acceleration. That's actually a very smart way of measuring the force. We take the same object, we apply the same force, but we measure how much it's actually accelerating. That's very, very clever. Muki is saying, okay, rougher surfaces have more friction between them. I 100% agree. And heavier objects have more friction because they press together with a greater force. I 100% agree as well. So Kay is saying it depends on the density of the object and the amount of particles that are touching the object. So something to do with like if it's touching the object more, it's gonna have more friction. And you can test this by sliding the same object over a different surface to test this. So also very good idea so far. And here's another really good idea, which I really like. The surfaces have different frictions because of the surface area. So something to do with like, asphalt has a lot of bumps and rocky parts. while ice is very, very smooth and has like very little imperfections. So something to do with like, the shape, the surface area, the density, the amount of particles that the object has. And you can do this by, you can slide the object, same object on both surfaces, and you can measure the acceleration on both of these surfaces. So honestly, I think you pretty much nailed it. The amount of friction a surface has depends on basically how smooth the surface is, right? The smoother the surface is, for example, ice, right? The less bumps there are, the less divots there are, the less cracks there are, the less like stuff there is to resist the object's motion. Whereas a bumpier surface like asphalt essentially means that there's more grip the surface has. There's more like ways the surface has to contact the object to slow it down, to grip onto the object. So the amount of friction a surface has depends on basically how smooth the surface is. Now, how much friction a particular surface has, this is what we use. This is what we use something called a coefficient of friction. So us scientists and engineers, we use something called coefficients of friction to show how much friction a particular surface has. So continuing our discussion on friction, there are two main kinds of friction. There is kinetic friction, which is friction that's related to friction on a moving object. So this is probably the friction you're familiar with. If an object is moving, then you're going to have friction that sort of goes against it. There's another kind of friction called static friction. And static friction is the friction an object exerts on a stationary object to prevent it from moving. So the reason why if I leave like a water bottle on the table, the reason why it doesn't move is because there is friction on the table and that's keeping it from moving. So in order to start this water bottle, in order to make it move, you have to apply enough force to overcome the static friction acting on it. Once you are able to apply enough force to keep it, to start it and keep it moving, I apologize. Once you apply enough force to keep it moving, there's no more static force friction acting on it, and instead kinetic friction takes over. So you basically have static friction keeping an object from moving, preventing it from moving. In order to make it move, you have to apply a force onto it to overcome the static friction, and then the kinetic friction will sort of take over as a result. So TLDR, kinetic friction, static friction. Kinetic friction is friction that is moving, and static friction is friction that is on a stationary object. Friction only exists on a surface, like if yes. So friction only exists on a surface. If my object is levitating, my computer, if my object is hovering in the air, there's no friction, right? Because it's not in contact with anything. It has to be in contact with something in order to have a friction. Yes, 100% correct. And so how much and the type of friction it has depends on whether or not the object is stationary or if it's moving. If it's stationary, it's currently under the influence of static friction. And in order to overcome that static friction, you have to apply a force in order to make it move. Once it's moving, kinetic friction sort of takes over that. Okay, so we only have 3 minutes left. I'm trying to decide if I have enough time to finish through this. So, okay, so I'm going to try to get through as much of this as I can, but I'm realized that I probably won't be able to get through all of it. So kinetic friction applies when the object is moving, as I was saying earlier, and it's the friction induced by the surface to resist the object's motion. What's interesting about kinetic friction is that the object is not moving, right? There's no kinetic friction. Instead, there is static friction. There's no kinetic friction. How much kinetic friction an object has is determined by the coefficient of kinetic friction and the normal force of the object. The coefficient of kinetic friction is a constant. It's just like a number that is dependent on the surface. and the normal force of the object. Basically, how much is the surface pushing onto the object? So if you have a heavier object, you're going to have a bigger normal force. So you're going to have a bigger kinetic friction force. And if you have an object with a higher coefficient of kinetic friction, it's going to have a higher frictional force as well. And the coefficient of kinetic friction is just a constant. For example, ice has a coefficient of kinetic friction of about 0.03. So a very small coefficient. Asphalt has like a coefficient of like 0.7. So rougher surfaces have bigger coefficients, and smoother surfaces have smaller coefficients. How is the coefficient determined? The coefficient is determined by measuring it. You are basically measuring the ratio. It's really a ratio of the friction force to the normal force. That's what the coefficient really is. So honestly, the way that all of you have estimated how you measure friction force, that's exactly how real engineers do it. You take an object, take an object, you slide it across different surfaces, and then you compare the frictional force that you measure to the normal force that you measure. And that ratio between the frictional force you measure and the normal force you measure, that ratio is the coefficient of friction, of kinetic friction. So if I have the same object and I have the same applied force and I have the same normal force, the difference in frictional forces will give you a different ratios between the friction force and the normal force, and that ratio is how you determine the coefficient of kinetic friction. So if my frictional force is half the normal force of my of a surface, right? Then that coefficient is going to be 0.5. You will never have to calculate the coefficient. Well, you will never have to like. I will sometimes ask you to find the coefficient by saying, okay, if I have a frictional force of this, and if my normal force is this, try to find the coefficient. I will never actually like empirically make you measure the coefficient itself. It's just something you'll determine from your friction or from your normal force. But that's just sort of a gist of how you measure it. So we are out of time, unfortunately. We actually got through a good amount, so I'm actually very happy with how much we got through. We will pick this up on Thursday. In terms of your homework, what we would the main homework assignment we will be working on is the free body diagram and Newton's second law assignment. Unfortunately, on that assignment, there are quite a few friction problems on there. That will not be due until next week, and I don't think we will start it until Thursday. If you want to take a stab on it and take a stab at maybe the questions that don't involve frictions, that's not a bad idea. But there's no real homework that's being due soon because we haven't really finished covering friction. So and TLDR, there's no real homework. If you want to take a stab at the free body diagram and Newton's second law assignment, you can, but we will actually start it on Thursday. Other than that, I'm very happy with where we are. Thank you all for participating. That'll be it for today. I will see you all on Friday. And we'll finish the graphic organizer and finish everything else on Friday. So
Thank you.
Thank you all.
Thanks.
Do we turn this in on Canvas or do we wait until Thursday to do that?
Wait until Friday.
Oh,
Yeah.
okay.
Thanks a lot.
Thank
Have a
you.
nice one.
Have a nice day.
Thank you.
Thank
Farewell. Bye-bye.
Thank you.
Thank you.